Today's lecture is brought to you by Stacks. It is on expression parsing, how to parse simple mathematical expressions in infix or postfix or prefix. So, first of all, what are infix, postfix, and prefix? Infix is the way most of you are familiar with writing out a mathematical expression. So you write something like 3 plus 4 times 7, and that gives you a nice, easy-to-human-read expression. And, of course, this being a computer program we're embodying this in, I'll use asterisks for multiplication throughout this talk, because we're going to be feeding these kinds of strings to computers and getting them to parse them. Then there is also prefix, and most of you are familiar with prefix because most of you took 61A. So prefix notation is when you write the expression before the things it's applied to. So this same expression is written plus 3 times 4, 7, and that's the natural way to express things in scheme, which is why a lot of you have seen it. And what it means is you add the next two operands, the first operand being 3 and the next operand being a compound operand. Postfix works the same way, except that with postfix, you have the two operands first, and then you have the operator that tells you what to do with them. You don't see postfix so much these days, but when I was a little kid, some of the calculators that were coming out still used postfix expression arithmetic. You had to actually know postfix and write postfix to use some of the early calculators. How do you interpret a postfix expression? Well, again, the idea of postfix is that you write an operator after its operands. For example, the simplest thing you could do is just something like one number, another number, and then what to do with those two numbers, multiply them. But each operand isn't just restricted to be a number. Each operand can be any postfix expression. And so, for instance, I can write down something like 1, 2 plus 3, 4 plus times. And what are the operands of that multiplication operation? Well, here's one of them, and here's the other one. Now, if you wanted to make this totally clear to a human how this is interpreted, you could parenthesize it. You could write paren 1, 2 plus, paren 3, 4 plus times. And this makes it easier for a human to read. But the interesting thing about postfix is that you never need the parentheses to clarify what an expression means. They're always optional, and a computer just doesn't need them. This is a completely unambiguous expression, as opposed to, say, an infix expression where it means something very different if you parenthesize it like this than if you parenthesize it like this. So anyway, this expression is the same as, well, 1 plus 2 is 3, 3 plus 4 is 7, multiplied, which is 21. So that's the value of that postfix expression. So now here's an algorithm for how you evaluate this formally. We're going to use a stack of numbers. It's just the natural way to parse a postfix expression. In fact, the early calculators that used postfix expressions actually stored the numbers in a stack as you entered them. So the algorithm is, we read the expression from left to right, process one number or symbol at a time. And we behave two different ways. When we encounter a number, we always just push it onto the stack. And when we encounter an operator, that's where the interesting things occur. We've got several things to do. First of all, pop the top two numbers off the stack. Because those are the two numbers we're going to operate on. And then perform the operation. And it's important to remember here that when you push two items onto a stack and then pop them off later, they come off the stack in the reverse order that you push them on. And therefore, your operands are now backwards. So you need to remember to treat the first number popped off the stack as the second operand. To make up for the fact that you've reversed the order of the two numbers on the stack. And finally, once you've done the operation, that gives you a number, you push that result back onto the stack. So that it is ready to contribute to the next operation. So, to see an example of this in action, let's look at the numbers 2, 7, 5, minus, times, 8, 5, minus, times. There's a postfix expression. We want to compute its value. So there's our empty stack. First we read a 2. The 2 goes onto the stack. Then we read a 7. Then we read a 5. Then we read a minus. So that means we pop off the top two operands. 7 minus 5 is 2. So now we have two 2's on the stack. Then we have a multiply operation. So those two 2's get popped, multiplied, and the result, 4, goes back onto the stack. And then we have an 8. And then we have a 5. And then we have a minus operation. So 8 minus 5 is 3. And then one final multiply. And there's our value that we wanted to compute sitting on the stack. And now we just have to pop it off and print it. Are there any questions about this? Yeah. Well, I think that this actually is still in use in a lot of, for instance, CPUs. A lot of floating point units still use a stack-based method of handling the operands, including in the, I think, modern Intel processors still do that. For, say, what? Well, it's not used in calculators directly anymore because people who use calculators prefer to type things in infix. But it's still used indirectly a lot because, as we'll see next, when you want to interpret an infix expression, the easiest way to do that is convert it to a postfix expression and then run this algorithm. So actually, I think they're used a lot still. And they're used. This kind of thing is also used a lot in compilers for parsing code, parsing the expressions in your Java code, for instance. It's used a great deal. So this is real practical stuff that people do use. Are there other questions? So the code that you have in front of you in your handout, if anyone doesn't have a handout, there's still some sitting over there. Does what I just told you about. So there's two main pieces of code to look at here. First of all, look at the method called operate. Well, here it is ahead of you. Let me give you the sunlight. All right. So this is the operate method. And it starts off by popping the operands off of the stack. As you might guess, the operate method's job is just to do one calculation when we get an operator. So the operator hits us, we call this method, and it does the operation for us. So first of all, it pops the operands off of the stack. We know those two numbers now. Then there's just a switch statement which, based on the circumstance that we find ourselves in, does whatever operation the symbol says we should do. Plus, minus, times, or in this case, I'm using this symbol here, the caret symbol, for exponentiation. That's not actually the exponentiation symbol in Java. Java doesn't have one. It is the exponentiation symbol in Fortran. So we're going to use that here. I've left out division just to keep the code from getting ridiculously long. And so, but what this does is it just does the obvious operations, adding the numbers, subtracting, multiplying, exponentiating, whatever, and then it just pushes the result back onto the stack. And what we also have here is the main routine is a little piece of code that you can play with, if you like. So the idea of the main routine is that it reads a postfix expression and evaluates it for you off the Java command line. And the way that you run this program is you type Java, and then the name of the class, which is parse postfix. And then in right quotes, you put the string that you want to parse. And this is a super simple, stupid program, so it only accepts single-digit numbers. So that's interpreted as 7, 3 times 2 plus. And then the program will respond by typing the string out again, which will be more useful in the second half of this lecture, and then printing out the result of the value of that expression. And so the way this main procedure works is it just has a very simple character loop that loops through all the characters in that command line input once. And what that character loop does is, at each character, it checks whether or not it's a digit. And if it is a digit, then you just push it onto the stack. On the other hand, if it's an operator, then that's where all the interesting stuff happens, and we've already seen the method that takes care of that stuff. So for an operator, we actually operate on the top 2 items on the stack. And so that's how that's done. Any more questions before I go on? Yeah. What is that C, 36? What this does is it takes the character C and it treats it as if it's a base 36 number and converts it into a number on that basis. So in base 36, you have the digits 0 through 9 representing themselves. Then you have the letters A through Z representing 10 through 35. And so the idea of this is this just allows me to compute on more numbers than just the digits 0 through 9, since it's lame enough that it only deals with one-digit numbers. But yeah, this is a handy thing to know about, though, if you want to interpret a hexadecimal number, for instance. You can set this to 16, and then it will convert your hex digits to numbers for you. Nice and easy. All right. So that's postfix. Postfix is easy. Now we want to move on to infix, which is a little harder. And by far the easiest way to evaluate an infix expression is to convert it to postfix along the way, and then evaluate that postfix expression as you go. So that's what we're going to do today. Now, one of the things that makes infix painful is the fact that it has precedence rules. And the precedence rules can get really complicated in languages like Java, which has a really complicated set of precedence rules. Basically, the problem is if you have something like the string I wrote up there, 3 plus 4 times 7, do I interpret that as being 3 plus 4 first and then times 7, or do I do the multiplication first? And of course, we have rules we all learned in math class that say, well, you do the multiplication first. That's wrong. And if you want to do the addition first, you need to throw in parentheses, which we're not going to handle today, but are easy to handle. So I want an infix parser that at least knows what the precedence rules are and follows them. So it knows that multiplication always binds more tightly than addition. Now, the precedence rules we're going to deal with, since we've only got 4 operators today, are relatively simple. They are exponentiation comes first. Remember, exponentiation is the caret character. So that has precedence over everything else. Including divide if we bothered to implement it, which we didn't. And those have precedence over addition and subtraction. But multiplication and division are equal, and add and subtract, we'll say, are equal as well. So when you have things that are equal in precedence, then you need a subsidiary rule to decide how to put parentheses around those. And that's expressed in the manner of, is an operator left associative or is it right associative? So most of the operators we care about are left associative. Plus, minus, times, divide. And left associative means that if I write 2 minus 3 minus 5, I really mean 2 minus 3. So we do the left one first, and then minus 5. If it were right associative, you'd get a very different answer. But not everything is left associative. Exponentiation is right associative. If you're wondering why exponentiation is right associative, it's because if I write something like 2 to the 3 to the 4, if I wanted it to be left associative, 2 to the 3 all taken to the power of 4, that's actually the same as 2 to the 3 times 4. So it's not really that useful to have it be left associative, because then you can only express things that you would prefer to express in a simpler, more clear form anyway. And so that is why when you just write something like 2 to the 3 to the 4, mathematicians always interpret that as 2 to the, well, do 3 to the 4 first. Because that way you actually get more useful power out of your mathematical writing. So exponentiation is right associative, and if I write 2 to the 3 to the 5, then I take 3 to the 5th power, and then I take 2 to that power later. Okay, well, with these rules in mind, we're going to convert infix to postfix, again, using a stack. This time, though, we're going to have a stack for the operators so that we can reorder them so that they get executed in the order we want in postfix. So our algorithm for infix, like our algorithm for postfix, is going to read the expression from left to right. And during this time, when we encounter a number, we just print it out immediately. When we encounter an operator, as usual, that's where all the hard work occurs. The idea is that we're going to take that operator and we're going to put it on a stack until somewhere down the road, an operator with lower or equal precedence appears. Unless that operator has equal precedence and happens to be exponentiation, in which case we wait even longer. And when that operator with lower or equal precedence finally arrives, then we pop and print the current operator. So this is actually a funny way of expressing the algorithm. It says an operator comes in, push it on the stack, and then wait until something else happens. But actually, we need to handle it in the code when that something else does happen. So when an operator comes in, you check it against the next operator on the stack. And if that operator on the stack has higher precedence, it's time to pop that operator. So we're going to do this once for each item in the string. And eventually, we're going to reach the end of the string. When we reach the end of the string, it's time to unload the stack. Any questions about this? Yeah.
When the operator comes with lower precedence, what happens to that when you're popping lower on the stack?
If an operator comes along with lower or equal precedence, then whatever operator is on the stack gets popped and printed. And then when we're done with operators on the stack, like there's no longer an operator of higher precedence on the stack, then you go ahead and you push the new operator. So the new operator always gets pushed no matter what. All right. So the brief question is, why? I sort of want to give you a few mini examples of what can be going on during this process. The simplest example is, suppose that what comes in is just 3 times 2, just to get started. That's your string on your way input. Then what happens is the 3 comes in and immediately gets written back out, because that's what we do with the numbers. The multiplication comes in and goes on the stack. The 2 comes in and immediately gets written out. And now we've reached the end of the string, so there's nothing left to do but pop whatever's on the stack and write it out. So obviously, for the simplest case, it works. What about a case where we have more than one operator, and when the second one comes along, the newest operator has lower precedence? Well, in that case, maybe it looks something like 3 times 2 plus. So what happens? 3 comes along, the times goes on the stack, 2 comes along, and then, well, here's the thing. As soon as you see this plus, you know that this times is going to bind more tightly than the plus. You know that we are going to add 3 times 2 to something else, because that's the precedence rules we use as humans. So that means that the times can be output immediately, and the plus goes on the stack after we pop off the times. And so once we've written this out, we push the plus and continue to read the rest of the string. And finally, maybe it goes the other way around. So maybe the newest operator has higher precedence. For instance, we have 3 times 2 to the power of. I don't know what the rest of the string is going to look like, but as soon as I reach this point, I know that this exponentiation operator binds more tightly than the multiplication. So I do not yet know what's going to get multiplied by 3. Multiply 3 by something that starts with 2 to the power of who knows what, but I don't know what yet. And so the multiplication has to stay on the stack until I find out what the second operator of the multiplier is. So we're going to write out the 3 and the 2, but the other 2 operations have to stay on the stack. So and so the idea again is that the multiplication stays on the stack until its second operand is complete. So any questions about those rules now? Yeah.
Once we pop the power off the stack,
Mm-hmm.
we pop the times as well, or do we wait for another operator?
So, I don't think that okay, it'll depend on what the next operand is, actually. So, or will it? Okay, well, this is kind of a special case just because times is left associative, exponentiation is right associative, and they happen to be right next to each other in precedence. So it just so happens that, yes, when the exponentiation gets popped off the stack, so will the times. But that wouldn't be true in general in all cases. Like, for instance, you might have a case where there's a plus on the stack and a times on top of it, and when the next times comes along, if the next operation is a times, then the times will get popped off and the plus will still stay on the stack. And we could have a whole series of things we're multiplying, and that plus has to stay there until they're all done. So the plus basically is there until the next plus or minus comes along in that case. Yeah, good question. It's tricky. So let me give an example now of what happens, what this algorithm does to infix 3 times 5 plus 4 to the power of 5 to the power of 6. So we start with an empty stack. Along comes a 3. Well, this is an operator stack, so nothing goes on the stack. What happens is our output, now we've got a 3 written to the output. As soon as we read the 3, we just write it back out again. No waiting with the numbers. Then we have a times. So the times goes on the stack. Then we have a 5. Well, doesn't change the stack again. The 5 just gets written out immediately. Then we have a plus. So the plus has lower precedence than the times. So the times immediately gets written out, and then the plus gets pushed onto the stack. And 4 gets written out immediately. Exponentiation goes onto the stack. 5 gets written out immediately. What's next? One more exponentiation. Number 6 just gets written out. And at this point, the string is over, so we just take whatever's left on the stack, and we pop them one by one and write them to the output. And so on the bottom row here, you can read our new postfix expression. Now, if we want to know the value of that expression, we can just go through it with the first algorithm I showed you, and we've got that number. Questions about that? All right, so coming back to the handouts I gave you a main method at the end that converts an infix expression to postfix. And evaluates the postfix at the same time. So what this code does is it interleaves the two computations. Because you can see that the infix to postfix computation is producing numbers and operators as we go, often long before we get to the end. And so as soon as those numbers and operators get produced, we can immediately feed them to the postfix algorithm. And that's what that code does. So the code works with two different stacks at the same time. One for numbers, one for operators. And let's take another look at that. So here's the main method that you've all got in front of you. Once again, there is now a really big loop that goes through and processes all the characters one by one. And if the character that comes in is a digit, then, well, first the infix to postfix algorithm passes it right through, unchanged, immediately. So we can immediately process it with the second half of our algorithm, the postfix evaluator, which means we push it right onto the number stack, just like we did before. On the other hand, if we get an operator, things are a little more complicated. Now what we're going to do here is we're going to look at the item on top of the stack, if there is one. We always check first to see if the stack is empty. And we're going to compare the precedence of whatever's on the stack with the operator we're looking at now. And so that's what this code is. This looks at the precedence of the number on top of the stack, the precedence of the new character that we've just read in from the input, and asks, is the one on the stack have greater precedence? And if it does, it's time to take that character on the stack and pop it off and print it to the output. Which, here's the pop, and, not print to the output, operate with it. So we pop an operation off the stack if its precedence is high enough, and then we do that operation with the code that I showed you before. So the operator, when an operator appears, what we do is we look at the other operators that have already come in and been stored on the stack, and we apply those other operators if it's appropriate to do so. And once we've popped off all the operators on the stack that need to be operated, then we push the new operator onto the stack. So that's what that loop does. And finally, when we get down to the bottom of the loop, when we're done, when we have no more input to read, then it's time to take whatever operators are still on the stack and do those operations. So we're going to pop those, we're going to print them, because this program outputs two things. It outputs the postfix version of the expression and the result. So we pop and print the operators that are still on the stack, and we also perform those operations. So, any questions about this marvelous expansive code? There's one other little piece to it, which is the actual precedence table. We need to have a way of looking up the precedence of different operators. And so this is just a case statement that looks at all the different possible operators and gives them each a precedence. Exponentiation is 3, multiply divide is 2, plus minus is 1. What's handy about this is that you could expand this. You could add another 50 operators to this table really easily. So you don't need to have a really complicated piece of code that negotiates all the operators against each other. You just have to assign each operator a number once. That's its precedence. And then you can have a million operators if you want, and the code will just take care of their precedence for you. And that's the lecture. Any final questions? All right. Thank you.